Excalidraw has this really cool feature that caught my attention, the elbow arrow connector. You might have noticed how these connectors never overlap the shapes or go across the nodes. Instead, they automatically find a clean path around everything. When I first saw that, I was super curious of how does that even work. So I decided to dig a little deeper and try to recreate it myself. And it turns out Excalidraw uses a pathfinding algorithm, something like A star, to calculate these smart connector paths. I'd used pathfinding before in other projects, but I never thought it could be applied in a diagramming tool like this. That was honestly fascinating. So in this video, we'll build our own version of that system, a connector that automatically avoids the nodes and finds the best path around them. It's not 100% perfect yet, but it already does the main job beautifully. We'll be using pixie.js for rendering, mostly because I wanted to experiment with it, but the algorithm itself will work in any environment. So if you're using another library or framework, you can still follow along easily. Alright, let's begin. To create a new pixie.js project, just run this command npm create pixie.js at latest, then run npm run dev. You should now see a basic pixie.js canvas appear in your browser. Next, we'll update the HTML and add a bit of CSS. Just a small control section with a button and some basic styling. Everything's simple to follow, and if you'd like, you can copy the same setup. Now let's move on to the main.ts file. And honestly, this part is pretty simple as well. So first, we're importing a few functions and setting up some basic constants, like the width and height for our nodes, and also grabbing a button from the HTML using its ID. This button is what we'll use to add new nodes on the screen later. After that, we wrap everything inside an async function. That's basically where our main code will live and start running. Inside this function, we're creating our pixie.js app, setting the background color, and attaching the canvas to our HTML container. We also create an empty array called obstacles, which will store all our nodes as we create them. That way, we can later tell our connector to avoid these obstacles while finding its path. Now we add an event listener to the Add Node button. Whenever we click it, we'll create a new node on the screen, add it to the stage, push it into the obstacles array, and finally call update connector to refresh our connection lines. Alright, now just below that, we're creating two sample nodes, one on the left and one on the right. So we have something to start with. We'll also create a debug layer and a connector line between them. The debug layer will help us visualize paths and obstacles while we test our algorithm. So at this point, we've got a basic setup running, two nodes, a connector, and the ability to add more nodes dynamically. From here, we'll move on to the interesting part, actually finding the path between these nodes while avoiding all the obstacles. Now in the next part, we've created a helper function called createNode. This function is responsible for drawing a simple node or box on the screen and also making it draggable. Inside it, we start by creating a new graphics object from pixie.js. Then we call beginFill with a color and use drawRoundedRect to draw a rectangle with rounded corners. Here we're drawing the rectangle using drawRoundedRect. Notice that I use -w/2 and -h/2 for the starting point. That's to keep the node centered at its position. So whenever we move or rotate it, it behaves from the middle, not from the top left corner. And the last value 10 gives the rectangle smooth rounded corners. After that, we set the node's X and Y position, make it interactive and set the cursor to pointer so it feels clickable. Then we handle the drag logic. We track a simple dragging flag. It becomes true when the mouse goes down and false when it's released. During the pointer move event, if dragging is active, we get the current mouse position relative to the node's parent container and update the node's position accordingly. And finally, we call update connector function, which will refresh any connection lines between nodes whenever one moves. This function then returns the node so we can add it to our stage or container. Now next, we have our update connector function. This function is responsible for drawing and updating the connection line between the two nodes. Basically, whenever a node moves, this function gets called to refresh the connector. First, we clear any previous line using connector.clear, and then we set a line style. Here it's a white line with a thickness of 4 pixels. Next, we calculate the start and end points for our connection. The start point is just slightly outside the right edge of node A, and the end point is slightly outside the left edge of node B. That small offset helps the line look cleaner. It doesn't overlap with the box edges. After that, you'll notice a commented out section for a step or orthogonal line. That's just an older version we tried earlier. Then we call a function named buildCandidateGrid. This one just shows a grid for visualization, but we'll come back to it later when we dive deeper into the pathfinding logic. The main part here is where we call a find connector path start end obstacles. This is the core function that calculates the best path between the two nodes, automatically avoiding any obstacles. We're going to explore that one in detail next because that's where most of the logic happens. Once we get the path, we move the drawing cursor to the first point and then connect all the points one by one using line 2. Finally, we call draw arrowhead to draw a small white arrow at the end of the connector. Now let's look at the draw arrowhead function. This one is a small helper that draws the arrow shape at the end of our connector line. It takes the current endpoint and the previous point, then calculates the angle between them using math.artan2. That gives us the correct direction of the line, no matter which way the nodes are positioned. Using a bit of trigonometry, we then draw two lines forming a small triangle. That's our arrowhead. The size is set to 12 and it's filled with white color to match the main line. So every time the connector updates, this function ensures the arrow at the end always points in the correct direction.
The first thing we need is the direction of the line. The code does this in one powerful step. Think of this line as a laser beam shot from Prev to A. The angle variable captures the compass bearing of that laser. It tells us the line's absolute orientation in the world. In our example, the laser is pointing straight right. Angle equals 0 radians or 0 degrees. Next, we need two things: the size of the arrowhead, which we set to 12 pixels, and the anchor point. The anchor is crucial. It's the tip of the arrow, A. All our drawing will pivot and be measured backward from this point. We need to find the coordinates of the two back corners of the triangle. Let's call them B, the upper wing, and C, the lower wing. Let's look at the calculation for the B point. The first part, angle minus pi over 6, is where we rotate our laser beam in pi over 6 or 30 degrees. If the main laser is at 0 degrees, this new angle is negative 30 degrees. This sets the angle for the upper wing. The rest of the formula starts at x, our anchor A, and uses the sine and cosine of that new angle to define the movement. Because we subtract x minus offset, the vector components from the tip A, we are forced to move backward along that rotated direction. This single calculation effectively says, start at the tip A and move 12 pixels backward along a path that is 30 degrees off the center line. The second wing, C, is found using almost the exact same line, but we add the 30 degrees to the angle. This gives us the mirror image, placing the second wing point below the center line. Finally, the last few lines simply connect the three calculated points. This closes the shape and fills it in, giving us a perfect arrowhead that correctly rotates around its tip, no matter which direction the original line is pointing. That's how we transform two simple line points into a full arrow structure.
Now we're getting into the most important part of this system, the pathfinding algorithm. Let's open up the pathfinding.ts file. To build the A-star pathfinding algorithm, we first need to define some helper functions and types that we'll use later in the process. So, as you can see below, we start by defining two types. First, point, which simply holds x and y values. Second, rect, which includes x, y, width, and height. Here the rectangle rect represents a node on our canvas, and note that it's center based, meaning x, y refer to the center of the rectangle, not the top left corner. Then we define a small constant called EPS, which stands for epsilon. It's just a very tiny value, 1 times 10 to the minus 6, that helps when comparing floating point numbers, basically to avoid precision errors when checking geometry values. Next, we create the rectBounds function. This function takes a rectangle R node and calculates its bounding edges, that is the left, right, top and bottom positions, based on its center, x, y, and its dimensions, width, height. These boundaries can later be used to check whether a point is inside the rectangle or to detect collisions during pathfinding. Optionally, we can also provide a pad value to slightly expand the rectangle's boundaries, which is useful if we want to keep a small buffer space around the node during pathfinding. Alright, so now let's quickly look into these three functions. The first one is pointInsideRectStrict, and this function simply checks whether a point lies inside a rectangle's boundary. So basically, if the points x and y values are between the rectangle's left, right, and top bottom bounds, then it's considered inside the rectangle. The strict part means it does not include points that are exactly on the border. It only counts points that are fully inside. We also add a tiny EPS epsilon offset to avoid floating point precision issues, and there's an optional pad parameter to slightly expand or shrink the rectangle's bounds if needed. Next, we have the orientation function. This one is really important when we deal with line intersections or geometry checks. Well, it basically tells us the turning direction formed by 3 points A, B, and C. So it uses the cross product formula B minus a multiply by C minus S to figure out if the sequence of points turns clockwise, counterclockwise, or if they're collinear, like they are all on a straight line. For that, we check the result. If result is 0, then the points are collinear. If result is 1, then clockwise. And if result is 2, then counterclockwise. And again, we use EPS to handle floating point rounding. And finally, we have the onSegment function. This one checks whether a given point B lies on the line segment that connects point A and C. It doesn't just check the slope. Instead, it checks if B dot X and B dot Y are within the min and max range of A and C, with a small EPS margin. So if proof falls inside both those ranges, that means the point is right on the segment. This function is super useful when we're checking for intersections between lines, for example, when detecting if two connectors cross. Now we have a new function called segments_intersect, and this one's going to be super important because we'll use it to check whether two line segments cross each other. We already made helper functions like orientation and onSegment earlier, and here we're putting them to use. So let's understand what's happening. The function takes two line segments, the first one from P1 to P2, and the second one from Q1 to Q2. Then, using the orientation function, we figure out the relative direction of each pair of points. Basically, we're checking how the second segment lies in relation to the first, and vice versa. If the orientations are different on both sides, that means the two lines cross each other. Then we also check a few special cases, like when the points are collinear, meaning they're perfectly aligned. In that case, we use the onSegment function to confirm if any of the endpoints actually lie on the other segment. If any of those conditions are true, we return true, meaning the segments intersect. So yeah, this function handles both normal and edge cases, whether the lines cross normally or are lying on the same line, collinear. It can detect both. Next, we have line intersects rect, and this one checks whether a line segment passes through or touches a rectangle, in our case, a node. So first we check if any of the line's endpoints are inside the rectangle using pointInsideRectStrict. If yes, then we instantly know it's intersecting, so we return true. If not, then we move on to check if the line crosses any edge of the rectangle. To do that, we get the rectangle's bounds using rectBounds, and from that, we calculate the four corners: top left, top right, and bottom left. Then we check each rectangle edge by calling segments_intersect 4 times, once for each side of the rectangle. If the line crosses even one edge, we return true. Otherwise, if none of these conditions match, that means the line is outside and not touching. If so, we return false. So yeah, this function is kind of like the collision detector for our connector path. It helps make sure that when we draw a line between 2 points, we can easily tell if it's running into a rectangle, which later helps the A-star algorithm decide which paths are valid and which ones to avoid.
Alright, so now we need to build something really important, the candidate grid. And this grid isn't spread across the entire canvas like you might expect. Instead, it's created only around the nodes and the ports. That means it's way more efficient because we're only focusing on the areas where routing actually happens, not wasting time scanning empty space. So the main idea here is simple. We generate a bunch of useful points, places where our connectors could potentially bend or turn, and then we let the A-star algorithm search only between those points. This gives us those nice, clean, elbow-style paths that stay clear of the nodes. Now, first thing you'll see is this constant. This value controls how far we push the connection points away from the nodes. Basically, it creates a little gap, or what we call outer ports, so the connectors can come out a bit before turning. You can tweak this number if you want your connectors to start further out or stay tighter to the shape. Now, build candidate grid function, what it does, and why. So here's where we actually build the grid. Now, this function might look a little heavy at first, but it's actually doing something really smart. It's collecting all the interesting x and y coordinates, not every single pixel, just the useful ones. For each node or obstacle, it grabs the four corners, the midpoints of each edge, and also some outer ports. Those are just points slightly outside each side, created using that offset value we saw earlier. And then we also include our start and end connector positions. All these coordinates get rounded to 2 decimal places to keep things clean and avoid duplicate or slightly off values because of floating point issues. After that, we take all the unique x's and y's we collected and create a cross product, basically combining every x with every y. That gives us a nice grid of possible intersection points, all aligned to our nodes and ports. We also make sure to add the exact start and end points again at the end, just to be safe. We don't want those rounded off. Finally, we remove any duplicates using a map and return the final list of clean, unique points. So, what we get is this really compact and efficient grid that's focused only around the obstacles, perfect for our A-star pathfinding step. And because it's built smartly, the algorithm runs fast and the connectors look super clean. Now, the next helper function we have is this one. This one's pretty straightforward. It only allows perfectly horizontal or perfectly vertical lines. Since our elbow connectors move in straight lines, we don't want any diagonal paths sneaking in here. So first, it checks whether the segment is horizontal or vertical with a small tolerance EPS to handle floating point errors. If it's not one of those, it's immediately rejected. Then, it loops through all the obstacles and checks if this line would collide with any of them using our line intersects rect function. If it hits something, we know that segment isn't clear. Otherwise, it's good to go. And that padding value you see, that's like a small safety margin. It slightly expands the obstacles during the check, so our connectors don't stick too close to the edges. You can tweak it if you want your paths to have a bit more breathing room. And finally, there are 2 small helpers that we'll use in the actual A-star algorithm. The first one, Manhattan function, just calculates the Manhattan distance, which works perfectly for this kind of grid because all our paths move in straight horizontal and vertical steps. It's basically the number of blocks you travel in a grid city, right? No diagonals, just turns. And the second one, key of point function, creates a clean, rounded string version of each point. This is super useful for storing or comparing points inside maps, so the A-star algorithm can easily track which nodes it has visited or not. Okay, so now we are at the final function, and this is where all the pieces come together. This function is using something called the A-star algorithm, so before we dive into the code, let's quickly understand what this algorithm actually does. So like, what is a star algorithm? Imagine you are standing at a starting point on a map, and you want to reach your destination. There are obstacles in between, so you can't just walk in a straight line. Now, a star is basically a smart pathfinding algorithm. It tries to find the shortest and most efficient path from start to end. Think of it like Google Maps. It doesn't check every possible road randomly. Instead, it looks at which direction brings you closer to your destination and how much distance you've already traveled. It balances these 2 things beautifully. So let's look at the core idea behind the A-star algorithm. A-star works with 3 main concepts. First, G-cost, G-score, how far you've traveled from the start point. 2, H-cost, heuristic, how far you estimate is left to reach the end. Here we use something called Manhattan distance because our paths only move horizontally and vertically. So it's just x1 minus x2 plus y1 minus y2, 3, f-cost, f-score. This is the total cost. It's simply g-cost plus h-cost added. A star always picks the node with the smallest f value next, the one that looks most promising. So in short, it explores all possible routes, but always prefers the one that seems shortest and safest toward the goal. Let's look how it works, step by step first. It starts from the start node and adds it to something called the open set. This is a list of nodes we still need to check. Next, for each node, it checks all its neighboring points, in our case other grid points that connect in a straight horizontal or vertical line. Then it calculates the g-cost, distance from start, the h-cost, estimated distance to the end, and adds them to get the f-cost. Then it picks the node with the lowest F cost and moves there. It repeats this process, checking neighbors, calculating costs, until it finally reaches the end node, and once it reaches the end, it walks back using a came from map, basically a memory of which point led to which, and reconstructs the full path. So that's a star in a nutshell. It's like exploring all paths, but doing it intelligently, so it doesn't waste time checking areas that obviously go away from the goal. Okay, now let's look at how our code does the same thing. I hope when we are going to go through the code step by step, you will get the idea how this works. So, step 1. Building the grid first, we call build candidate grid function, which generates all the possible grid points we can move through. These points are placed around the obstacles, not across the entire canvas, so it's much more efficient. We then store all these points in a map using their coordinates as keys. Step 2. Creating adjacency. Next, we build connections between points that line up horizontally or vertically and don't collide with any obstacles. That's what the is-axis align segment clear function check is doing. We store all of these valid connections inside the ADJ map. So now, you can think of this as a graph. Every point knows which other points it can directly connect to. Step 3. Setting up the A star variables. Now we create all the main data structures like open is for the set of points we still need to check, came from is a map to track which point we came from. Next, G score, it stores how far we've traveled from the start, and F score, it stores the total cost. G plus H initially, all scores are set to infinity except the start point, which gets G score as 0, and F score is set to the Manhattan distance from start to end points. Step 4. The main loop. Inside the while loop, we pick the node from the open set that has the lowest F score. That's our most promising node. If that node happens to be the endpoint, we stop, we found the path, and then we reconstruct it by walking backward through came from. If not, then move to step 5, exploring neighbors. We remove it from the open set and check all of its neighbors from ADG. For each neighbor, we calculate a tentative G score, which is basically current.G score plus distance from current to neighbor. If this new path to the neighbor is shorter than any we found before, we update the neighbor's scores and record that we came from the current point. Then we add that neighbor back into the open set, so it'll be considered later. Step 6. Reconstructing the path. When we finally reach the end, we rebuild the full path by tracing back through the came from map from end to start, and then reverse it. Finally, we also remove any redundant points that fall on a straight line, just to make the path cleaner visually. And at last, we have a fallback case if no path was found. Maybe something's completely blocked. We simply fall back to a basic L-shaped elbow, start, horizontal, vertical, end. And if you want to learn more about this, there are plenty of videos on YouTube you can check out. I'd suggest watching a few of them. I'm sure you'll get the idea. Alright, so now everything is done. We've completed all the logic, and the final step is just to draw the path. In the main.ts file, we call the findConnectorPath function, get the list of points, and then use that to draw our final connector line. And that's it. Now you'll notice that the path always avoids the nodes perfectly and connects everything just the way we want, exactly as expected. If you'd like to follow along or use this code yourself, I've added the GitHub link in the description, so feel free to check it out. I really hope you learned something new from this video, and in the next one, we're going to explore something even more interesting. If you enjoyed this, make sure to leave a like, subscribe, and as always, if you have any questions or suggestions, drop them down in the comments. I'll see you in the next video.